So this is February-March 2022 question paper 2, waiting 2. The first question says, a sphere of radius 2.1 millimeter falls with terminal velocity through a liquid as shown. Three forces act on the moving sphere. The weight of the sphere 7.2 into 10 to the power minus 4 newtons, and the upthrust acting on it is 4.8 into 10 to the power minus 4 newtons. The viscous force acting on the sphere is given by Fv is equals to KRV, where R is the radius of the sphere, V is its velocity, and K is a constant. The value of K in SI units is 17. Determine the SI base units of K. So they've given us the formula, and they just want us to use that formula to get the base units. So we'll write down the formula, Fv is equals to KRV, and we'll plug in the base units for all the quantities involved. Fv, which is the force, has the SI unit newtons, but the base units for newtons are kilogram meters per second squared. K is the unknown quantity here. R is the radius, which is measured in meters. V is the speed or the velocity in this case, meters per second. K, make K the subject, kilogram meters per second squared divided by meter squared per second. This meters multiplied by this meters per second gives you meter squared per second. You simplify and solve for K. The units that you'll get are kilogram per meter per second. Part B of the question says, use the value of upthrust acting on the sphere to calculate the density rho of the liquid. Now, we know that the formula for pressure is force per unit area, or rho GH. So we'll start off with that if you don't remember the formula for force. So pressure is rho GH. And because force is pressure times area, this becomes rho GH times area. This here is volume. So force, the upthrust force, is rho GV. So you may either know this formula directly or you may derive it. What do we have here? We have the upthrust force given in the question as 4.8 into 10 to the power minus 4 newtons. 4.8 into 10 raised to the power minus 4 newtons. The rho is an unknown, G is 9.81, and V here, which is the volume of the sphere, can be found using the formula volume is equals to 4 over 3 pi r cube. 4 upon 3 pi, the radius of the sphere, as given in the question, is 2.1 millimeters. So we'll have to convert this into meters. So this becomes 2.1 into 10 raised to the power minus 3, the entire thing cubed. The value that we get is 3.88 into 10 raised to the power minus 8 meter cube. We'll use this value over here, 3.88 into 10 raised to the power minus 8. And after making rho the subject of the equation, we will find out the density of the liquid, which comes out to be, let's see, 1261 kilograms per meter cube. Rounded off, what do we get? 1300 kilograms per meter cube. C part 1 says, on the sphere in figure 1.1, draw the three arrows to show the direction of the weight W, the upthrust U, and the viscous force Fv. Label these arrows W, U, Fv respectively. So moving back to figure 1.1. So figure 1.1 tells us that the bubble is the sphere, in this case, sorry, not the bubble, the sphere moves downwards with a constant velocity. One thing that I know for sure is that the weight acts downward. The upthrust, as the name suggests, acts upwards. the viscous drag acts in the opposite direction to motion. So because the sphere is moving downward, the viscous drag acts in the upwards direction, Fv. This is how you draw the arrows. C part 2 says determine the magnitude of the terminal constant velocity of the sphere. Now, the constant velocity of the sphere, as given in the question, can be found using the equation Fv is equals to K R V, which is given here. Fv is equals to K R V. Now, the problem is we don't have the viscous force, but we can find out the viscous force, because the viscous force is plus the upthrust. The viscous force plus the upthrust is equal to the weight. We can use that to calculate the viscous force. So let's do that first. Fv plus the upthrust is equal to the weight. Do we have the upthrust? Yes, we do. Is equals to W minus upthrust. What's the weight? The weight is 7.2 into 10 to the power minus 4. What is the upthrust? The upthrust is 4.8 into 10 raised to the power minus 4. And that gives us the viscous force, which is equals to 2.4 into 10 raised to the power minus 4 newtons. Now we'll use that viscous force over here in our first equation. The question says that the constant K has a value 17 in the SI units. So the constant K will be replaced by the number 17, which is the value of K. The radius R is 2.1 millimeters, so 2.1 into 10 raised to the power minus 3 times V, which is the velocity. We'll make V the subject of the equation and solve for V. The speed or the terminal velocity comes out to be 6.7 into 10 raised to the power minus 3 meters per second. Question 2 says water leaves the end of a hose pipe at point P with horizontal velocity of 6.6 meters per second as shown in figure 2.1. Point P is at a height h above the ground. The water, this is h above the ground. The water hits the ground at point Q. This is point Q. The horizontal distance from B to Q is 3.5 meters. Air resistance is negligible. Assume that the water between P and Q consists of non-interacting droplets of water, and the only force acting on each droplet is its weight. So for this entire motion, the only force that is acting is the weight on of the water. Explain briefly why the horizontal component of the velocity of a droplet of water remains constant as it moves from P to Q. So why is it that the horizontal velocity does not change? Because there's no horizontal acceleration, which is what horizontal velocity being constant means. But what do you write here? You simply write that the reason is that there is no force acting in the horizontal direction. Part B says show that the time taken for a droplet of water to move from P to Q is 0.53. So you can either go with the vertical component and the vertical height, but we don't have the vertical height, so we can't calculate time using the vertical vectors like velocity, acceleration, height, displacement. What we'll use instead is the horizontal velocity along with the horizontal distance. Because the horizontal velocity is constant, we can simply use speed is equals to distance over time, or S is equals to UT, which is basically the same formula. Speed is 6.6, the distance is 3.5, and time here is the unknown. The value of time that you get is 0.5303, which is 0.53 seconds, and this is what they wanted us to show. 2 part C says calculate the height h. Now that we have the time it takes for water to move from P to Q, so irrespective whether you talk about the horizontal component, if I say that it takes this water leaving the pipe 0.53 seconds to travel a horizontal distance of 3.5 meters, that's correct. Or if I say it takes 0.53 seconds for the water to travel a vertical distance of h, that is also correct. Time can be used interchangeably. So what do we do here? This time around, we'll go with a different equation because we're solving it in the vertical direction and there's acceleration in the vertical direction. S is equals to ut plus half at squared in the vertical direction. What is the displacement? H. What is the initial velocity? 0. Because the initial vertical velocity is 0, the water leaves in the horizontal direction. Plus half into acceleration, which is 9.81, t squared, which is 0.53 squared. The answer that we get is h is equals to 1.378 meters. Rounded off, this is 1.4 meters. Part D of the question says, for the movement of a droplet of water from P to Q, state and explain whether the displacement of the droplet is less than, more than, or the same as the distance along its path. Is the displacement the same as the distance? So what are they actually asking? Let's go back to our diagram. They're actually asking that if we take this displacement, which is basically a straight line from P to Q, is this displacement greater than the actual distance, which is this curved path, or is it less than, or is it equal to? Now we can clearly see, and we know that for a fact, that if you travel in a straight line, that distance, which is known as displacement, is obviously the shortest distance. So what do we write here? We'll write, for part D, we say the displacement is less than the distance because it is in a straight line. Part E says, calculate the magnitude of displacement of a droplet of water that moves from P to Q. So for a droplet of water, it travels a horizontal distance of 3.5 meters. It travels a vertical distance of 1.4 meters. They're asking you for this displacement, which is basically the hypotenuse. So using Pythagoras' theorem, this is displacement. We'll say the displacement squared is equals to 1.4 squared plus 3.5 squared, which is equals to 3.8 meters. Question number 3 says, a jet of water hits a vertical wall at right angles as shown in figure 3.1. Horizontal jet of water density 1 into 10 to the power 3 kilograms per meter cube. You're given the cross-sectional area of this jet. You're given the velocity with which it moves. The water hits the vertical wall with a velocity of 5 meters per second in a horizontal direction. The cross-sectional area is 1.5 into 10 to the power minus 4 meters squared. The density of the water is 1 into 10 to the power 3 kilograms per meter cube. The water runs down the wall after hitting it. Show that over a time of 1.6 seconds, the mass of the water hitting the wall is 1.2 kilograms. Now, they want us to calculate the mass. We know that mass is density times volume, or mass is density times the cross-sectional area times the length. We do have the density, we have the cross-sectional area. The problem is length. Now, you need to understand that what they're actually talking about is a cylinder of water, and the length of that cylinder of water depends upon the time duration for which the water is turned on. So let's take this diagram that we have here and try to understand how the length changes and how can we use that to find the volume. Now, if you look at this, the cross-sectional area is constant. This is the cross-sectional area. This length depends on the time and the velocity. The velocity is 5 meters per second, which means for every 1 second that this water is turned on, you get a length of 5 meters. Our water jet is turned on for 1.6 seconds. So the total length that we get, the total length is 5 meters per second multiplied by 1.6 seconds. The seconds cancel out and you get 8 meters. Now plug in the values. You've got the density. The density of this water is 1 into 10 to the power 3. You've got the cross-sectional area, which is 1.5 into 10 raised to the power minus 4. You've got the length, which is 8 meters. You'll get the mass as 1.2 kilograms. Part B of the question says, calculate the decrease in the horizontal momentum of the mass of the water in A due to hitting the wall. Now what happens to this water is, as it hits the wall, it just runs down the wall. So it loses all of its momentum. So all we need to do here is calculate the initial momentum, because that is what it loses. How do we calculate the initial momentum? Momentum is the product of mass and velocity. The mass is 1.2 kilograms. The velocity is 5 meters per second. The momentum comes out to be 6.0 Newton second. 6.0 is the answer. B part 2 says, the magnitude of the horizontal force exerted on the water by the wall. What is the force exerted? Now, force is equal to the rate of change of momentum. Do we have the change in momentum? Yes, 6. The momentum lost is basically the change in momentum. Divided by the time, this is the time duration for which you had the change in momentum, and that is 1.6 seconds. So 6 upon 1.6, which is equals to 3.8 newtons. Part C of the question says, state and explain the magnitude of the horizontal force exerted on the wall by the water. So what we found first earlier in the previous part was the horizontal force exerted on the water by the wall. The force exerted by the wall on the water would be exactly similar, which is equals to 3.8 newtons. And why? According to Newton's third law. Part D says, calculate the pressure exerted on the wall by the water. What's pressure? Pressure is force per unit cross-sectional area. What's force? The force is 3.8 Newton. The area is 1.5 into 10 raised to the power minus 4 meters squared as given in the question. You'll get the pressure as 2.5 into 10 raised to the power 4 pascals. Question 4 says a child moves down a long slide as shown in figure 4.1. The child moves from rest at the top end X of the slide. An average resistive force of 76 newtons opposes the motion of the child as they move to the lower end Y of the slide. The kinetic energy of the child at Y is 300 joules. The decrease in gravitational potential energy of the child as it moves from X to Y is 3200 joules. So of the gravitational potential at this point, 3200 joules, what has happened is that at Y, due to the resistive force, you're only left with 300 joules of kinetic energy. The rest of it gets converted into thermal energy because of the resistive forces. Determine the ratio of the kinetic energy of the child at Y when the resistive force is 76 newtons, which we know is 300 joules, upon the kinetic energy of the child at Y if there is no resistive force. If there were no resistive force, this 3200 joules, which was basically the gravitational potential energy, would get converted into kinetic energy. All of this would get converted into kinetic energy. So 300 upon 3200. What do you get? You get 0.094. This is the ratio. B says, use your answer in A to calculate the ratio of the speed of the child at y when the resistive force is 76 newtons to the speed of the child at y if there are no resistive forces. And so we have the relationship, we have the ratio of kinetic energy. They want us to calculate the ratio of speeds. We know that kinetic energy is equals to half mv squared. Because half is a constant and so is the mass of the child irrespective of whether there are resistive forces or not, Ek is proportional to v squared. So we can clearly say that the ratios of the kinetic energy is proportional to the ratios of the velocity squared. So let's say speed when there are resistive forces upon speed when there are no resistive forces. The entire thing squared is equal to the ratio of the kinetic energy, 0.094. Square root both sides and you get this ratio of the speed of the child when there are resistive forces to the speed of the child when there are no resistive forces. This comes out to be 0.31. Some of you may go with some other approach like Ek is proportional to v squared. Kinetic energy when there were resistive forces was 300. The speed at that point, let's call that Vf squared. And the kinetic energy when there are no resistive forces, 3200. The speed at that point, let's call that V. V squared. They want us to calculate Vf squared, Vf upon Vf upon V. So you use that, Vf upon V is equals to square root of 300 upon 3200, which is basically the same thing. Part C says, calculate the length of the slide from X to Y. What is the length of the slide? What do we know here? We know that 76 newtons, this is the resistive force. Do we know the work done against these resistive force? Yes, we do. We expected 3200 joules of kinetic energy. We got 300 joules of kinetic energy, which means the difference, which is equals to 2900 joules. This is the work done against friction or against the resistive forces. And the formula for work done is force times displacement, or force times distance moved in the direction of that force. So 2900 is equals to force, which is 76, times the distance. Distance is equals to 38 meters. That's the answer to part C. Part D of the question says, at end Y of the slide, the child is brought to rest by a board as shown in figure 4.2. A spring connects the board to a fixed point. The spring obeys Hooke's law and has a spring constant of 63 newtons per meter. The child hits the board so that it moves to the right and compresses the spring. The speed of the child becomes 0 when the elastic potential energy of the spring has increased to a maximum value of 140 joules. Calculate the maximum compression of the spring. So they have given us the energy of the spring. They have given us the spring constant of the spring. We'll use the formula potential energy or elastic potential energy, EP, is equals to half kx squared, where k is the spring constant. 140 is equals to half k, which is 63, and it's an SI unit, so no conversion needed, x squared. Make x the subject of the equation and solve for x. We get x is equals to 2.1 meters. This is the compression. Part 2 says, calculate the percentage efficiency of the transfer of kinetic energy of the child to the elastic potential energy of the spring. percentage efficiency. They're asking you for the ratio, but they want it in terms of percentage. What is the elastic potential? What was the elastic potential energy stored in the spring? 140 joules. What was the kinetic energy of the child at that point? The kinetic energy of the child was 300 joules. This is the ratio. Since they want percentage efficiency, this is the efficiency. Since they want percentage efficiency, you multiply this by 100. So 140 over 300 times 100 is equals to 47%. Part 3 says the maximum compression of the spring is x naught. On figure 4.3, sketch a graph to show the variation of the elastic potential energy of the spring with its compression x from x is equals to 0 to x is equals to x naught. How does the elastic potential energy of the spring change as the compression increases? Now, what I think, some students would go with a straight line, because in the question they did mention that it obeys Hooke's law. So they'll most probably get confused between the graph of force extension and energy extension. To understand how you draw the graph, you need an equation that links both these quantities. And that equation is Ek is equals to half kx squared. Because half is constant and k is constant, Ek is proportional to x squared. Some of you may argue, why can't we use the equation Ek, not Ek, Ep, sorry. Why can't we use the equation Ep is equals to half fx? That gives us Ep is proportional to x, but that is not the case because the force will not be constant. The force changes, so you can't eliminate force, and hence you cannot use this equation. You'll have to use this one. Once you figure this out, you need to draw a graph of y is equals to x squared. That is what they're asking. So the graph would look something like this. A curve starting from the origin, and the gradient of the line increases. Question 5 says, state the conditions required for the formation of stationary waves. For the formation of stationary wave, you need two waves of the same frequency / wavelength traveling in opposite direction along the same line and overlapping. Part 2 says, state the phase difference between any two vibrating particles in a stationary wave between two adjacent nodes. So you've got a node here, you've got an adjacent node here. This is a loop. They're asking you, what is the phase difference between any two particles between these two adjacent nodes? We know that any two particles in a loop between two nodes have a phase difference of 0 degrees. Adjacent loops have a phase difference of 180 degrees. Part B says, a motorcycle is traveling at 13 meters per second along a straight road. The rider of the motorcycle sees a pedestrian standing in the road directly ahead and operates a horn to emit a warning sound. The pedestrian hears the warning sound from the horn at a frequency of 543 Hz. The speed of the sound in the air is 334 meters per second. Calculate the frequency to three significant figures of the sound emitted by the horn. They've given you a question on Doppler effect. You'll use the formula. Observed frequency is equals to speed of sound upon speed of sound minus speed of the source times the source frequency. So this here at the bottom may either be negative or positive depending on whether the source is moving towards the observer or away from it. So since it's moving towards, we'd use a negative sign. If it was instead moving away, we'd go with a positive sign. Do we have the observed frequency? Yes, we do. It's 543. Speed. Do we have the speed of sound? Yes, it's 334 upon 334 minus the speed of the source, which is 13 meters per second, times the source frequency, which is an unknown. We'll solve for Fs, the source frequency, which comes out to be 522 Hertz. Part 2 says the motorcycle rider passes the stationary pedestrian and then moves directly away from her. As the rider moves away, he operates the horn for a second time. The pedestrian now hears sound that is increasing in frequency. State the variation, if any, in the speed of the motorcycle when the rider operates the horn for the second time. Now, this is a good question, I'd say. What's happening here is, for the same pedestrian, the motorcyclist, a poorly drawn one though, the motorcyclist is now moving away. When it's moving away, if it was traveling at a constant speed, the frequency that he would hear would be lower than the actual frequency, but it would be a constant value, a lower value but a constant value. The question says that the observer or the pedestrian hears the horn for the second time, and he hears the sound that is increasing in frequency. It's increasing in frequency. We'll use our formula again. F naught is equals to V upon V plus Vs Fs. If the observed frequency is increasing, that basically means that the denominator here is decreasing. If this is increasing, this should decrease. Fs is constant. Speed of sound is constant. In fact, even in the denominator, this V, which is the speed of sound, is constant. So the only way that the denominator can decrease if Vs, the speed with which the motorcyclist is moving, decreases. So we'll write the speed is decreasing. Clear. Part C of the question says a beam of vertically polarized monochromatic light is incident normally on a polarizing filter as shown in figure 5.1. This is the vertically polarized light, intensity I0. This is a polarizing filter at 20 degrees. The transmitted light beam has an intensity IT. The filter is positioned with its transmission axis at an angle of 20 degrees to the vertical. The incident light has an intensity I0 and the transmitted light has an intensity IT. By considering the ratio IT over I0, calculate the ratio amplitude of transmitted light over the amplitude of incident light. Let's write it as AT over A0. Now, there are two ways to solve this. You can either use the formula IT is equals to I0 cos squared theta and rearrange this. You've got the angle as 20 degrees, find out the ratio of IT over I0, and then you can use I is proportional to A squared. So the square root of that previous ratio would basically amplitude squared. So the square root of the previously ratio would give you the ratio of the amplitude. Or you can say A is equals to A0 cos theta. Do this directly. I is proportional to A squared. So AT over A0 is equals to cos theta. AT over A0 is equals to cos 20. Just find out the value of cos 20. Make sure your angle is in your calculator is in the radian mode. The answer comes out to be 0.94. Part 2 says the filter is now rotated about the direction of the light beam. From its starting position shown in figure 5.1, the direction of the rotation is such that the angle of the transmission axis to the vertical initially increases. Calculate the minimum angle through which the filter must be rotated so that the intensity of the transmitted light returns to the value that it had when the filter was at its starting position. Now, what are they asking us to do? They're saying that this polarizing filter that you see is rotated, and it's rotated in such a way that the intensity of the that the angle, here we go, where is it, that the angle initially increases, which basically means that this here will be rotated in this direction. The filter will be rotated in the clockwise direction if you view it from this point. Now, how much do I need to rotate it so that I end up with the same value as is right now? For that, it's important that the transmission axis is once again at 20 degrees. But this time around, the transmission axis would be at 20 degrees over here at the bottom. So if this is 20, this is 20, and this entire thing is 180 degrees, I'll have to rotate it by an angle of 140 degrees so that I end up at the same place. Question 6 says the ends of a metal resistance wire are connected to a battery of EMF 8 volts and negligible internal resistance as shown in figure 6.1. So this is the 8 volt power supply. This is our resistance wire. The power dissipated by the resistance wire is 36 watts. Calculate the current in the resistance wire. So we know that the formula for power is VI. The EMF of the battery is 8 volts. Because there's no other load in the circuit or no other resistance in the circuit, there's no internal resistance, our resistance wire experiences a potential difference of 8 volts, which is equal to the EMF of the battery. So 36 is equals to 8I. I is equals to 36 over 8, which is equals to 4.5 amperes. Part 2 says, the number of free electrons that pass through the resistance of the wire in a time of 50 seconds. How many free electrons pass through the wire in 50 seconds? Now, the value of current that we calculate, what is current? Current is total charge flowing per unit time. So I can find out the total charge that flows in a time of 50 seconds. So current is 4.5, the time is 50. This is equal to 225 coulombs. This is the total charge. Now, they're not asking us for the total charge, they're asking us for the number of electrons. It's a simple ratio from this point. One electron has a charge of 1.6 into 10 raised to the power minus 19 coulombs. How many electrons have a charge of 225 coulombs? X is equals to 225 over 1.6 into 10 to the power minus 19. Some of you may not feel the need to write this down and may do this directly, but this you can use this ratio, or you are using this ratio even if you do it like this. So the number of electrons come out to be 1.4 into 10 raised to the power 21. Part 3 says the resistance of the wire. We have the voltage, potential difference, we have the current, we have the power. We can use any of the formulas. You can either say V is equals to IR, V has a value of 8, I has a value of 4.5. Let's find out R. We may use power is equals to I squared R. We've got the power, we've got the current, we'll get R. We may use power is equals to V squared over R. We've got the power, we've got the potential difference, we'll get R. So R comes out to be 1.8 ohms. 1.8 ohms. Part B says, the metal of the resistance wire in the circuit has a resistivity of 1.4 into 10 to the power minus 6 ohm meter. The cross-sectional area of the wire is 0.25 millimeter squared. Determine the length of the wire. The formula of resistance, including resistivity, is R is equals to rho, where rho is the resistivity, L the length, upon the cross-sectional area A. The resistance of the wire is 1.8. The resistivity is 1.4 into 10 to the power minus 6. The length of the wire, which they want in meters, is L. The cross-sectional area is 0.25 millimeters squared. We'll have to convert millimeter squared into meter squared. So 0.25 into 10 raised to the power minus 3. But because it's millimeter squared, this would be the conversion. This 10 to the power minus 3 would be the conversion from millimeters to meters. But because this is squared, we'll write it as into 10 to the power minus 3 squared, or directly, you can write it directly as 10 to the power minus 6. L is equals to 0.32 meters. Part C says the circuit the circuit shown in figure 6.1 is modified by replacing the original resistance wire with the second resistance wire. The second resistance wire has a greater diameter than the original wire. There are no other differences between the second wire and the original wire. By reference to the resistance, state and explain whether the power dissipated by the second wire is more than, less than, or the same as the power dissipated by the original wire. So what have we done here? We have changed a few things when we added the second wire. It has a greater diameter, and it's made of the same material as the original wire. Now, power is equals to V squared over R. Irrespective of the resistance connected here. So you may have a 1.8 ohm resistor like we have here, or we may have an 1800 ohm resistor. Irrespective of that resistance, the potential difference across that resistance would be 8 volts, because that's what the battery here is capable of providing. The current will vary, but the potential difference stays the same. That is why we're going with the formula for power that has potential difference as opposed to current. Now, P is proportional to 1 upon R, because V squared is constant. Now, the second wire has a greater diameter. It has a greater diameter, which means that it has a greater cross-sectional area. It is made of the same material. Because it's made of the same material, it will have the same resistivity. It has the same length. So that does not affect the resistance. The only thing that did change our resistance is the diameter. So greater diameter, greater cross-sectional area means that the resistance is lesser. We can see that from the formula we've written above. When the cross-sectional area decreases, the resistance increases. R and L are constant. So the resistance of the second wire is less because of the larger cross-sectional area. But our question was, explain whether the power dissipated, how does it affect the power? That is what the question was. So if the resistance is less, the power dissipated would be greater. Thus, more power dissipated than the original wire. Part D of the question says the circuit shown in figure 6.1 is modified by connecting a second battery of EMF 8 volts and negligible internal resistance in parallel with the original battery and the original resistance wire as shown in figure 6.2. So the only difference here is they've added another battery of 8 volts in parallel. You've got the original wire that had a resistance of 1.8 ohms. Nothing else changes. By reference to the current in the resistance wire, by current in this wire, state and explain whether the addition of the second battery causes the power in the original resistance wire to decrease, increase, or stay the same. Now, even though we've added another battery in parallel, we know that power is equal to V squared over R. And when you have batteries connected in parallel, irrespective, identical batteries connected in parallel, like in this case, irrespective of the number of batteries, the total potential difference to the circuit does not change. So this is 8 volts, this is 8 volts. This resistance wire here still gets 8 volts. So it has the same potential difference. It has the same resistance, so it will have the same power. But they want an answer in terms of current. So V is equals to IR. Despite the addition of this second battery, the V is unchanged. The resistance is still 1.8. So the current in the wire is the same. So the power stays the same, because power is equals to I squared R also. Current is same, resistance is same, obviously power would be same. Now one question that you may have in your mind is, what difference did the second battery now make? There should be some difference now, because we've added another battery. Now the difference here is the current, which originally was, what was the current? The current originally was 4.5 amperes. So the current originally was 4.5 amperes, and it's still 4.5 amperes. In the original case, where you had one battery, that battery provided 4.5 amperes. In this case, because you've got two batteries, each battery provides half of that. So you get 2.25 amperes from this battery, you get 2.25 amperes from this battery, and the resistance wire still gets 4.5 amperes. No change to that. Question 7 says a nucleus of sodium 22 decays by emitting a beta plus particle. A different nucleus is formed by the decay. State the name of another lepton that is produced by this decay. So whenever you have a beta plus or a positron decay, you have an electron neutrino or a neutrino being produced. On the other hand, if you had a beta minus decay, you'd have an antineutrino or an electron antineutrino. Part 2 says determine the nucleon number and the proton number of the nucleus that is formed by the decay. So sodium decays into something, and along with that you've got a beta plus particle and an electron neutrino. Now for this daughter product that is formed, the nucleus that is formed by this decay, if you balance the equation, you'll realize that the number on the top is unchanged, and that is what always happens with the beta plus decay. The number at the bottom decreases by 1, because this is 10 plus 1. Whenever you've got a beta plus decay, the proton number decreases by 1. If you have a beta minus decay, the proton number increases by 1. So what's the nucleon number? 22. What's the proton number? It's 10. Part 3 says the quark composition of a nucleon in the sodium 22 nucleus is changed during the decay. Describe the change to the quark composition of the nucleon. Now, whenever you have a beta plus decay, an up, down, the up, down quark composition changes into up, down, down. Basically, one up changes into a down. B says a baryon consists of quarks that are same flavor type. The charge of the baryon is -2e, where E is the elementary charge. Calculate in terms of E the charge of each quark. Now baryons consist of 3 quarks, and 3 quarks that are identical in this case will obviously have the same charge. So Xe plus Xe plus Xe is equals to -2e. These are the 3 identical baryons that we have, with each baryon having a charge of Xe. You can solve for X, or you may not feel the need, you can do this directly. X is equals to -2 by 3 E. So -2 by 3. So -2 by 3 plus -2 by 3 plus -2 by 3 is -6 by 3, which is equals to -2, which this is what they want. State a possible flavor of the quarks. Now you need to know what flavors have a charge of -2 by 3. So up quark, charm quark, or top quark. These 3 quarks have a charge of +2 by 3e, +2 by 3e. On the other hand, down, strange, and bottom have a charge of -1 by 3e. We need a charge of -2 by 3e. So the anti-quarks of these 3 will have a charge of -2 by 3. So any one of these, because they are identical, all 3 quarks have the same flavor, so you may either write anti-up, or you may write anti-charm, or you may write anti